All right, so let's concentrate on the case in which U is U is a diffusing thing. It's diffusing and it's spreading out in space via Fick's law. So the two-dimension diffusion equation is the t derivative of U is equal to alpha times the Laplacian of U. And the question that I ask is, in the steady state, what does this solution become? Well, what does steady state mean? Steady state means U is not changing with respect to time. It's steady. And so in the steady state, the t derivative of U is equal to 0. So if the t derivative of U is equal to 0, this equation becomes 0 is equal to alpha times the Laplacian of U, but I can just divide both sides by alpha, and I get this is equal to the Laplacian of U, or Laplacian of U is equal to 0. And for reasons that we'll talk about in a few weeks, really the operator that people mostly want to work with is the minus Laplacian. But of course, if the Laplacian is U, the minus Laplacian is U. So in this case, whether you choose plus or minus, it doesn't matter. And a function that satisfies this, so definition, if the Laplacian of U is equal to 0 on some domain omega, then we say U is harmonic. On omega, I guess that's part of the definition. So if a function's Laplacian is equal to U on some domain omega, we say that it is harmonic on that domain. Okay, let's talk a little bit about harmonic functions. So if U is harmonic, on omega, and again, we're assuming that this is a diffusing, U is something that diffuses, something that obeys Fick's law. Wait, hold on a second. I don't want to start this video over, so I'm just going to adjust this right now. I have a tripod, it makes it a little bit better, but still I'm using a webcam and I probably should, I'm not using the right tools. At any rate, so if U is harmonic on omega and we're assuming that it satisfies Fick's law, then the net flux is going to be equal to the line integral around the boundary of omega. I don't know why I put it over there. I thought I had an omega drawn over there. It's going to be the line integral around the boundary of omega of the normal derivative. Well, so let me just write it like this. It's going to be the flux. Okay, but what is flux? Flux is going to be equal, flux is proportional to U. So this is going to be minus alpha, or it's proportional to the gradient of U. This is minus alpha times the gradient of U dotted with n. Okay, but now we can use the divergence theorem. This is minus alpha times the integral over omega Laplace U dA. But if the Laplace of U is equal to 0, well, that is, if this is equal to 0, then this is equal to 0. So what it says is that for a harmonic function, there is no net flux. So this might, let's say this is omega, and we've got flux. Let's say these are our flux lines. So it doesn't mean that stuff is not flowing in or out of omega. It just means whatever flows into omega is exactly balanced by whatever flows out, and so then whatever flows out is exactly balanced by whatever flows in. This is sort of a defining property of harmonic functions, that they're steady, that the net flux is 0, they're in a steady state solution, the net flux is 0. This is a defining property of harmonic functions. Okay, now when dealing with harmonic functions on a domain, there are several different types of problems that we can deal with. So you might remember when we've looked at partial differential equations so far, we have the PDE, which is like Laplace U equals 0, but there's also some sort of boundary condition or initial condition or something like that. So let omega be a domain, This could be a bounded domain or an unbounded domain. It could be like a blob like we've been drawing, or it could be all of R2. It could be the upper half space of R2, things like that. So let omega be a domain. Then we have these two problems, and there's more, but there's two kind of main ones I want to talk about. There's a Dirichlet problem. The Dirichlet problem asks to find a function that is harmonic on U and and is given prescribed values on the boundary of U. Okay, so if this is omega, here we know that the Laplacian of U is equal to 0. And on the boundary, we know that U is equal to G. So if U is the temperature of this plate, the steady state solution is going to be when we have a steady state temperature, like the temperature isn't changing. So if U represents, if U is the temperature and the Laplacian of U is equal to 0, this is the steady state temperature. Okay, so what does this mean then? If we know that U is equal to some prescribed value along the boundary, it's like saying we're somehow, however we're doing it, we're holding the temperature constant along the boundary here. We're holding the temperature constant along the boundary, or not, well, constant in time along the boundary, whatever G is equal to. Okay, and then the temperature distribution in here is going to be whatever it is in that situation. So it's like the long-term temperature distribution. If we're able to hold the boundary at a certain temperature and just kind of let this experiment run on, the temperature is going to go to it's going to go to the solution to this equation here. The function whose Laplacian is 0 on the interior and who is equal to these prescribed values on the boundary. And so for Dirichlet, for the Dirichlet problem, this is prescribed temperature. Okay, there's another problem, the Neumann problem. I always want to do a Seinfeld impersonation here since this sounds like Newman. So we're going to have the Laplacian of U is equal to 0 on omega, and now you want the normal derivative of U to equal some prescribed function on the boundary of omega. Okay, now the computation that I had up here shows that the derivative, if I do the derivative of this around the boundary of omega, it's equal to 0. So the only way this can make sense, the only way that this can possibly have a solution, is if the integral of G around the boundary is equal to 0. So let me write it in this strange way. If the integral of G around the boundary is equal to 0, because if U is harmonic, we know the integral of the normal derivative of U around the boundary is equal to 0. Okay, so in this case, what we're prescribed, is how the temperature, how the heat is flowing out of the boundary. So for Neumann, it's how heat is flowing outside of the boundaries. Okay, now the particular case is going to be when the boundary is insulated, in which case the flow is 0, the flux is 0. So if the boundary is insulated, this would mean the flux of U across the boundary is equal to 0. In other words, G is equal to 0. Okay, and I didn't mention it, but in the heat case, well, in all cases, we're assuming nothing is flowing in this direction. So we're always assuming that like the top of the disk and the bottom of the disk are bound, or the top of the plate and the bottom of the plate are bounded. in the insulated in the heat equation so that heat isn't moving in this direction. Okay, so these are kind of the two special problems that we look at when we talk about, these are the two special problems that we look at when we talk about the Laplacian equation. We're not going to be able to, at this point in the class, we're not going to be able to find really good ways to find solutions to this equation, like with a function that we can actually kind of write down and do things with. I mean, you'll see what I'm talking about in a couple of videos. And then next week and the week after, we'll look at other ways to solve Laplace's equation. But this is all that I want to talk about now for this video.